This is the accompanying demo for our work, Goal-Oriented Semantic Communication for Robotic Arm Reconstruction in Digital Twin, Feature and Temporal Selections. This work is supported by Toshiba Europe Ltd and EPSRC. The existing wireless networks cannot fulfill the ever-increasing demand for digital twin real-time reconstruction, especially for robot arm reconstruction due to the high-frequency control and complex dynamics. Reconstructing industry-level robot arms in real time not only requires tremendous wireless resource, but also might cause traffic congestion and buffer overflow on the receiver end. In the conventional robot arm reconstruction framework, the physical robot periodically sends its current operation state to its digital twin for reconstruction. This message normally contains three features: its current joint angles, gripper state, and contact force between the gripper and target objects. However, this framework is inefficient in both the feature domain and time domain since a large number of less important data are transmitted. This motivates us to propose a goal-oriented semantic communication reconstruction framework. We first design a feature selection algorithm to evaluate the most important features from the original messages. That is, we filter out irrelevant features that do not contribute to the reconstruction process. Building upon this, we further design a deep reinforcement learning-based temporal selection algorithm to evaluate the importance of the message at current time slot and decides whether it is necessary to trigger its transmission. Our proposed framework transmits only the goal-oriented semantic information for reconstruction, thereby reducing the communication load without affecting the reconstruction quality. We first validate our framework in the PyBullet simulations. The robot arm we consider in this work is the Franca Research 3. It has 7 joints and an inbuilt 2-finger gripper. We compare our GSC framework, namely FS and PPDQN, under both strict and relaxed reconstruction error constraints with conventional frameworks. Under strict error constraints, the digital twin is expected to be reconstructed with at least 99.9999% accuracy according to the Industry 6.9 standard. Under relaxed error constraints, the digital twin is allowed to tolerate a higher reconstruction error, in exchange for a reduced communication load, where the reconstruction accuracy should achieve 5 nines. We consider 3 robotic tasks in this work. They are pick and place, pick and toss, as well as push and pull. All of them are commonly considered by the Robotic Society. Let's first check the pick and place task. The robot arm is designed to move a wooden cube from its initial position to a specified target location. It is observed from the bottom left figure that our GSC framework not only dynamically adjusts the transmitted features, but also decreases the number of transmissions. Therefore, it only requires transmitting a much lower number of bytes. It can also be seen from the bottom middle and bottom right figures that the reconstruction errors of our GSC framework under strict error constraints is relatively close to those of the conventional framework. The second task we consider is the pick and toss task, where the robot arm must throw the wooden cube accurately into a target area. Similarly, our GSC framework requires a much lower number of bytes to achieve the similar level of reconstruction accuracy. Importantly, it can be seen from the bottom 3 figures that the transmission interval, which is represented by the density of dots in the left figure, is dynamically adjusted according to the reconstruction error, with more messages being transmitted when the reconstruction error is larger. This shows the effectiveness of our temporal selection algorithm. The last task we consider is the push and pull task. The robot arm is required to open a drawer and then close it. We also validate our framework in real-world experiments, where we perform the pick and place task as an example. The physical robot arm is commanded by an external workstation PC via the C++ interface libfranca at 1 kHz. To capture the contact force, a gel site sensor is attached to the surface of the gripper pads, which is a gel-based tactile sensor that can perceive the shape change of the contact surface and identify 3-axis contact forces. The digital robot arm is deployed in another workstation PC running a PyBullet simulation. We obtain similar observations from the experiments, where our proposed GSC framework effectively minimizes the communication load while maintaining the reconstruction error at the same level as the conventional wireless framework. Notably, it can also be observed that noticeable reconstruction errors exist all the time in the experiments, which is different from simulations. This is because the simulator relies on ideal kinematics and dynamics models of the robot arm, but cannot capture external factors, such as joint friction, that might impact reconstruction accuracy in practice. Finally, we provide numerical results to show the effectiveness of our framework. In the pick-and-place task simulation, we reduced the communication load by 59.5% under strict error constraints and 79.5% under relaxed error constraints. In the pick-and-place task real-world experiments, we reduced the communication load by 53% under strict error constraints and 74% under relaxed error constraints. In the pick-and-toss task simulation, we reduced the communication load by 70.4% under strict error constraints and 86.2% under relaxed error constraints. In the push and pull task simulations, we reduced the communication load by 61.3% under strict error constraints and 81.5% under relaxed error constraints. Thanks for watching this demo. For more information, please refer to our paper.